Hello everyone, thanks for coming. I'm Robert Sherry. I'm here to present work we did on near-ultrasonic covert channels using software-defined radio techniques. I did it alongside my co-authors, Ethan Bain, who's with us today, and David Plus. So I'd like to begin by just discussing our research scenario a little bit. So if we have two computers infected with some sort of malware, be that by phishing, be that by some sort of exploit, how can they communicate once being detected without being detected? Because once you've actually got access to the machine, you want to try and preserve that for as long as possible as an attacker. But with an evolving network defense landscape, with things like intrusion detection systems and various other points to get detected, that's a risk. Just communicating over the network you're already on could give away that you've attacked a computer. So much like in nature, when something evolves to avoid defense mechanism, I think attackers will evolve to avoid this defense mechanism. And to me, an acoustic covert channel seemed like a good way to do this. So why use an acoustic covert channel? Well, audio is pretty fundamental to using a computer, right? I'm sure we've all spent the past 2 years on Microsoft Teams. I'm sure we all like to listen to music while we work. And if you took that away from a user, you wouldn't be particularly happy. So it's something that's fairly stable across a wide range of devices. Laptops and mobile phones have a microphone and speaker by default, and most desktop computers are provided to them in an office environment to allow for you to use things like Teams. Another factor is that if you make the sound high-pitched enough, nobody can hear it. So that means that it can go on without being detected, hence covert. Another key thing for us is that sound waves and radio waves are mathematically equivalent. Yes, the medium in which they transfer is different, but you can represent them both as a sine wave. And that offers some really cool techniques that you can use, because obviously radio technology has been developing for years and years to enable things like Bluetooth and Wi-Fi to provide high throughput connections that are usable. So what we thought was, if we take all this innovation that's been done in this space, such as software-defined radios, Bluetooth and Wi-Fi, this enables the possibility for you to create a really high-performance covert channel that's commonly available in a wide range of computers. So a covert channel is not a particularly novel idea. It was originally defined by Butler Lamson in 1973 as a communication channel that is not intended for communication at all. And what that means is, if you never considered something to communicate across it, you can't defend against it. And that's one way you could get around such defense mechanisms. Specifically, the idea of an acoustic covert channel is not particularly novel either. There are 6 prior papers on acoustic covert channels. However, all of them roll their own digital signal processing techniques. They all use a fast Fourier transformation to detect different frequencies and just simply decode the data there. And in doing that, very simplistically, they run into a bunch of issues with performance, range, convertness, and reliability that we felt could be improved. Notably, on the convertness level, when you're modulating the data in the way that we're doing, you run into clicking. Now, I don't know about you guys, if your computer start going click, 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 click very quietly, I'd be a little bit concerned that that would give away the convertness. So this led to our research questions. We wanted to explore what is the maximum performance of an acoustic covert channel. Yes, it's been done before, but not particularly quickly and not particularly at any range. And that really limits the scenario in which you can use it. What advantages using software-defined radio techniques provide over previous work? And what threats does this pose to traditional high security networks? So in order to describe how we improved upon prior work, I need to give a little bit of an introduction into modulation. Modulation is the process of encoding data into a wave, and there's 3 main properties of a wave you can vary to do this. First one is how loud are the amplitude. So a louder signal is a 1, a quieter signal is a 0. That works, but you run into problems with range, because the further you get away, the quieter and quieter the signal will get, and the smaller the gap. So that makes it not particularly great for this method. Another way is the phase. You can think of this of where the wave starts, basically. But in the sound domain, you run into the problem of that you have a bit of momentum, and that can make it hard to accurately recreate that signal. And one thing you run into is, again, the clicking, which doesn't really work for covert channels. As a result, most of the prior work, including this one, uses frequency shift key. Basically, you pick 2 pitches of a sound, high enough pitched, one's a 1, one's a 0, you decode it. However, in prior work, they have largely just arbitrarily picked the frequencies in which they use. So 19,000 hertz for a 1, 18,000 hertz for a 0. And what happens is that you will not always change at a good point. And that results in the clicking that I mentioned earlier. And in this video demonstration that I've done at audible frequencies, as not to hurt your ears in the room, you should be able to hear the clicking I'm talking about. So what you can see on the line there is that it rapidly jumped from somewhere in the line to the bottom of the line, somewhere between. And that causes the problem that I mentioned of clicking. What we used is a variant of frequency shift keying called minimum shift keying. What that does is that it ensures that you pick your frequency and your baud rate, or how quickly you're transmitting carefully. What this results in is that the change always happens when the wave is at 0. This results in no clicking, which will now keep much smoother, and you don't hear that quite audible click or distortion that you had earlier. The important thing to note is that even at ultrasonic frequencies, when you can't hear the tones that I'm talking about, that click still exists, and that's a big problem for coverts. Previous work got over this by using pulse shaping. So what they do is they make the signal quieter at the start, quieter at the end, and that sort of gets rid of the issue by hiding it by making the change very small. That works, but in doing that, you're sacrificing your signal to noise ratio. So you're not speaking loud enough for the entire tone, and people will be able to hear you. And it also compromises on how quickly you can go, because eventually you go so quick that the difference doesn't matter. It's still just like that. Demodulation sounds pretty easy. Like I said, you go high it's 1, low it's 0. But then the real world steps in and suddenly you have a bunch of issues. You need to filter out the signal. The microphone isn't going to give you a perfect signal. You're going to get the signal echoing around the room, and that's going to completely destroy whatever signal you had. You'll get issues with side channels. If you want to do duplex communication side by side, they can interfere with each other. And most importantly, you don't know when the transmitter is going to be sending anything. So you need to figure out when it's happening, decode it in time. And obviously, none of this is perfect. So you need some error correction to make sure you can actually get some good data on the other side. So rather than re-implementing years and years of software, radio, and digital signal processing ourselves, we decided to turn to a tool called GNU Radio, which is an open source toolkit that we use to develop a system. Essentially, you connect blocks together, it's very friendly, and applies algorithms to a signal, and then you can decode a signal. Now, normally this is used for software-defined radios, but we managed to apply it with a little bit of innovation to sound signals. And this is really key because there's lots and lots of algorithms that have been developed by incredibly smart people to solve for these issues that haven't been applied to this medium before. And that really lets us increase the throughput significantly to the point where you can actually excentrate a large file or communicate between two computers. So this is our implementation. As you can see, it's a flowchart as I described. And I'm just going to step you through what each block does and give you a rough idea of what we improved on. So top layer is our packetization layer. In the middle, we have a virtual Ethernet interface, and then it goes into a packing encoding block that is an open source extension to GNU Radio. What this gives us is encryption, it gives us error correction, and that really helps you make sure your signal is reliable. It then goes into a virtual sync, which is basically just linking it to the next line, where we use minimum shift keying. We then use a frequency translating filter, which takes it from 0 hertz, which is sort of baseband frequency for radio, and we upscale it to 20,500 hertz, which is also top, near ultrasonic, which you can't hear. We then just convert it to a real number, put it into an audio sync. We do lose some data in that process, but for the audio medium and modulation process we're using, it doesn't affect the reliability. For decoding, we take the signal into the microphone, we turn the floating number into a complex number, starting the imaginary component, and translate it back down to baseband. We then apply an equalizing algorithm, which what that does is it helps us correct for echoes around the room. We then apply an automatic gain control algorithm, which helps us ensure that the signal that the demodulation algorithm is receiving is a constant amplitude, which makes decoding much better. And then we apply demodulation, which then goes back into depacketization, back into the Ethernet interface. So that's the entire work there. It's kind of simple, but great. So in order to test it against the scenario we had, we decided that we wanted to test it against as many different scenarios as possible. So we had 3 levels of hardware on both the microphone and speaker, ranging from literally the cheapest headset we could find in the university, to some sort of prosumer Blue Yeti microphone and Logitech speakers that would give you as much advantage as you could realistically get in a sort of office environment. We tested at 3 different ranges, ranging from 3 to 9 meters, to see how far across an office could you get with this technique, how useful would you actually be able to use it for. We tested at 3 different baud rates to get an idea of what sort of the limits you can get from this, and 3 different frequencies to get an idea of how high can you go and how many signals could you get in the near ultrasonic range. We sent 10 kilobytes of known data across the channel. We recorded the number of valid packets received, and we could calculate the throughput and error rate. This is 243 different combinations, which I didn't quite realize at the time, but we got them all done. And we did it once each, relying on sort of the inherent repetition between sending multiple packets. And here are our results. This is sort of a snapshot. You can see the full thing in the paper, which will be published at the conference. We managed to demonstrate up to 656 bits per second at up to 9 meters. We found best performance was at around 18,000 hertz. When we thought about this, this makes a lot of sense because companies are not going to spend time developing for frequencies that no one's ever going to hear. So they're very much optimized for the sort of human speaking ranges of frequency. It's co-authored. You can see that better equipment improved in better performance, obviously, but in particular, the microphone was pretty important. So with the good microphone and terrible speakers, we could get a reasonable connection, but if the microphone was bad, all games were off. This is sort of important because the attacker could choose a microphone. You could use a high-end ultrasonic microphone and you could probably get some really good performance from that. And here's where our work really shines, I feel. It's in comparison to prior work. So probably the most natural comparison you can make here is to Zarandi and al. At 685 bits per second. It's important to note that this work doesn't actually work under our scenario. They use a phase shift gain, and audible clicking was noted as audible throughout the entire transmission, which in our eyes doesn't make it clever. The next highest one was the Schultz work in 2014, which is 345 bits per second, which is comparable to our lowest end implementation, but we can go even higher. And but the key limitation in that work is it's back-to-back phones. There's no range, so that's not really practical for our scenario either. After that, per hour's work at 230 bits per second is probably the most comparable. As you can see, we got results at 384, 496, and 656 bits per second, which are all far greater than prior work. Some of these work do have higher ranges than us, notably the Schultz work at 30 meters. We'd like to see future work done on the channel we've demonstrated here to demonstrate the maximum length. We were limited by the size of the lab we were in, so we couldn't go really any higher, unfortunately. So I'd like to discuss some countermeasures that we proposed to this sort of this technique. You could, at a hardware level, filter input and output devices to prevent them from using audible frequencies. This wouldn't really affect the user experience because they can't hear those frequencies anyway, so they're unlikely to be relying on them. The problem with that is cost. It's not really feasible for someone to implement this across a wide range of devices. It'd be hard to do on devices that use digital signaling such as USB. You could jam the ultrasonic spectrum by playing ultrasonic white noise. I don't think people in an office would be particularly happy with that. I'm sure they get quite irritated and maybe get that of a headache. There's been some work done on that and it's not particularly healthy. You can maybe use that in somewhere like a server room or something to prevent servers communicating, but those don't always have speakers, so it's questionable how useful that would be. The countermeasure we think would be most effective would be some sort of distributed monitoring system using software deployed on all computers. In this way, you could sort of log to a central database, such an intrusion detection system, that I've heard ultrasonic noise, that's a bit weird, then someone can look into it. The limitation on that one would be that some industrial devices use ultrasound to detect people in a room, for example, so that might not work in that sort of environment. Finally, a discussion on future work. So we managed 656 bits per second on one channel. It's important to note that we managed to do this in a much smaller bandwidth than other work. And what this means is that you could use multiple of these channels within the ultrasonic spectrum to multiply that effectively with very little problems. This is a technique called orthogonal frequency division multiplexing, and radio hopefully does actually just have support for that, which is always nice. So future work could go back to that and implement that and potentially get 2, 3, 4, 5 times the amount of throughput we got. You could use a mesh network to increase range. So that's just seen in prior work, but they had a very limited implementation, only allowing for 20 bits per second, which meant that any sort of command took like 30 seconds to send. We'd like to see a higher performance version of that. So that would enable you to communicate potentially across an entire office without ever touching the internal network, which would obviously be incredibly powerful. We'd like to see the maximum range of a link tested. So obviously we only test up to 9 meters. We've seen no sign that using sufficiently high quality equipment, you can go even further than that. Just like to see someone test the limits of what you could do with this technique in regards to range. We also like to see validation of the channel using random bursts of communication. So ours was one big long stream of data. We'd like to see short bursts of data, sort of like asynchronous testing on a hard drive to validate that if you send random communication, it still works well. We'd like to see some validation of countermeasures because as I said, as the malware evolves to avoid these sort of techniques, we'll need to see some sort of way to evolve back to defend against them. Thanks for listening.